Welcome to the first video in our third class time series of lecture videos. We'll begin with a little review. We talked about the formation of allyl lithium and allyl Grignard components at the end of our class 2 series of lecture videos. There we showed that things like N-butyl lithium could deprotonate our propene, give us allyl lithium reagents and butane, or you could throw allyl bromide in with magnesium and a nice ethereal solvent like tetrahydrofuran, THF, and generate allyl magnesium bromide. As a Grignard, if you recall, Grignards can react with electrophiles. They can definitely deprotonate water or the deuterium form of water, D2O, and incorporate deuterium in the allylic portions of our organometallic allyl lithium or allyl magnesium bromide Grignards. Here we have allyl lithium reacting with D2O to give us a deuterium on our allylic carbon and lithium deuteroxide. We could additionally think about forming carbon-carbon bonds with our allyl Grignards. Here we've got allyl magnesium bromide reacting with acetone to give us this allyl magnesium alkoxide, which after aqueous acidic workups gives us this tertiary alcohol that incorporates, our allyl system. So, with that out of the way, we can talk about a more complex pi delocalized system. Let's talk about dienes. A diene is a hydrocarbon with two double bonds, and so we can have conjugate dienes, that is adjacent double bonds. So the p orbitals on those four carbons are all part of the same pi system, and they overlap with each other, hence conjugate dienes. This particular one is trans 1,3 pentadiene. Here we've got a cis2 trans 4 heptadiene. You can even have them in cyclic rings. Here we've got a 1,3 cyclohexadiene. So conjugate dienes have overlap between the p orbitals and their pi bonds. Alternatively, non-conjugated dienes have no overlap between their p orbitals and pi bonds. So double bonds are separated by some saturated carbons, that is sp3 hybridized carbons. So you can see this Z14 heptadiene, or I guess you could call it cis14 heptadiene. Carbon 3 is saturated, it's a CH2. There's no p orbital on carbon 3, so it does not connect those pi systems. Here I've drawn those hydrogens out explicitly, but I assume everyone knows bond line diagrams by now and can count the number of hydrogens they would expect at any given carbon in a bond line diagram. Here's a 1,4 cyclohexadiene. This is a non-conjugated diene, right? Carbons 3 and 6 are saturated, they're CH2s. So very different from our 1,3 cyclohexadiene. Finally, to end this video, we've got accumulated double bonds, and so that's two double bonds that share one carbon atom, and those double bonds actually, their p orbitals do not overlap because of the geometry. So the two double bonds cannot share electron density because of the geometry of the p orbitals. You can see I've diagrammed it out right here. These two p orbitals that make up this pi bond are in the plane of the page, and these two p orbitals that make up this pi bond come out and go back into or behind the plane of the page, so that these sets of pi bonds cannot overlap. With that, I guess I'll see you in the next video.